stage in the design flow is physical design. So in which we refine the gate level design into a arrangement of circuit elements in an ASIC. It's nothing but now in synthesis we have discussed the functional design is converted into gate level design. Now here in physical design we are converting the gate level design into a final end product, nothing but ASIC here. So ASIC is nothing but application specific integrated circuit. Once the design is implemented in this ASIC, it is treated as a final end product. So that can be available on the market. Similarly, we can implement using FPGA. The change in the FPGA is that, so it acts as a prototype. So it allows the designer to redesign the functionality of a design. So first, we'll discuss the physical design for ASIC. So the physical design for ASIC consists of floor planning, placement and routing. So what is floor planning now? So in floor planning, it involves deciding where each of the blocks in the partition design is to be located on the chip. Is nothing but here decides the location of the blocks in the partition design. Okay, because this is important. So blocks are nothing but here. So these are the subsystems of the main system. So some blocks or the subsystems are connected with the external pins, and those external pins are interfaced with the outside world. So that's why the location of the blocks in a chip plays a very important role. The blocks that has large number of connections between them should be placed near each other, since that reduces the wire length and wiring congestion. So if the two blocks shares a maximum interconnection of wires, those need to be placed near to each other. That avoids the wire length. The next is blocks that are connected to the external pins should be placed near the edge of the chip, because they are connected to the external world, that is input-output devices. The position of those blocks also determines the allocation and positioning of pins for external connections. Now the next is blocks should be arranged to make the chip as close to square as possible. So if you are design the blocks in such a way that it should close to a square, because square chips are easier to package than rectangular chips. So because the final end product is always in terms of square or in rectangular. So in that, square chips are very easier to package, which is act as a final end product. So that's why the blocks should design which is close to square. Floor planning also involves the arrangement of power supply and ground pins and internal connections, and importantly the connection and distribution of clock signals across the chip, because the clock signals takes maximum area for the interconnection. So that's why here the arrangement of power supply and ground and internal connections is also important, because clock signals circuit is much larger in size or in area. Finally, the floor planning also involves the provision of channels for laying out interconnections between the blocks. Okay, so this is about floor planning. Similarly, when it comes to the placement and routing, so placement and routing involves positioning each cell in the synthesized design. Nothing but here positioning of each cell which are placed in the blocks. Okay, there are number of cells which are placed in the blocks. So those position of the cell are important, and that is done by the placement. And finding a path for each connection is nothing but routing here. Means interconnecting the cells in a or within a block is nothing but routing here. The main goals are to position all cells and route all the connections while minimizing the area and delay of critical signals. So proper placement and routing, we can minimize the area and the delay of the critical signals. So the result of placement and routing is a suite of files to send to the chip foundry for fabrication. So after the completion of placement and routing, we can send the chip to the fabrication. In fabrication, we will get the package which can be used as a final end product. So here, so this is the detailed timing simulation is a final check that our design meets its timing constraints. So this is a final check which is done in the placement and routing. That is, the design which is implemented as a package meets all the timing constraints. So once this is done, then it can be tested and sent to the market. So here the physical design for FPGA is also similar to the physical design of ASIC. So only the change is it contains mapping. So mapping is nothing but here in FPGA is provided with a many number of lookup tables. So lookup tables are nothing but it is used to store the known values. So mapping is used to map the mux or the gates which are used in the design. They are mapped for the lookup tables based on the functionality used in the design. So remaining concepts are similar here. So just go through this, you will understand the physical design for FPGA. So this is about physical design of an design flow. Okay, so if you have any doubts, you can send me a text. Thank you.